which is given by Rodolfo Rios-Zertuche, and he will tell us more about solving PDEs, variational and optimal control problems using semi-definite programs via occupation method relaxations.
Oh, okay, thank you. Yeah, thanks everyone for being here. Thanks to the organizers, really, for all this effort, and to the speakers for their wonderful talks. So, okay, so I'm going to talk to you about this work we did with Milan Corda. This year I spent it at LAS with a group of Jean-Bernard Lasserre, with Victor Magron and Milan, and this is the work with it together with Milan. So I first want to set up a global optimization problem for which the solution minimizes with the Lipschitz function. Okay, so for these Lipschitz functions, the domain will be an open set omega. That's nice. It's bounded. It has a piecewise C1 boundary that I denote partial omega, and its values, the values of the functions are on the set Y, which I will refer to as the codomain, and so the derivatives are on the set Z of n times m matrices. And this notation here is like the Sobolev space of type 1 infinity, but it's just basically the Lipschitz function. And in order to describe this optimization problem and its full richness and articulate all its nuances, we need many auxiliary functions, the Lagrangian for the bulk, the Lagrangian for the boundary, and then the conditions. This is going to be an equality condition, an inequality condition on the bulk and then on the boundary. And we will use some very mild complexity assumptions that you can ask about at the end. I will tell you the important ones. So the problem is just minimizing the integral of L on x, y of x, and the derivative of y for Lipschitz functions y, plus some integral also on the boundary with some equality conditions that can include the values of a function and also its derivatives. And so you have equality conditions, inequality conditions. So there's, of course, in practice, your favorite problem will only use a couple of these functions, and the rest you can set to 0. So please don't be scared and try to breathe. So, but what can you do with this? So I mean, right off the bat, you can see that if you set f to be a linear function of this dy of x, you'd have you're already solving an optimization problem subject to some quasi-linear equation, like the Burgers equation, so that's very nice. But as we learned in the calculus of variations course, a minimizer needs to satisfy what's called the Euler-Lagrange equation. And there's a wide range of partial differential equations that appear as Euler-Lagrange equations of problems of this type, like the elliptic equations, the heat equation, the relativity equations, the wave equation, the Schrödinger equation, the even Ricci flow. So our friends the physicists have spent many years looking for variational principles for basically all models in physics. You can write kind of like this. But not only that, there are also other classes of problems that you can express like this. Variational problems, obviously, but also optimal control problems, optimal transport problems. You can study asymptotic dynamics of continuous time vector dynamical systems. You can even do that with differential inclusions. With differential inclusions, you can work with games. You can do some game theory with for example, the best response dynamics are a differential inclusion. You can use the Branier approach to the Navier-Stokes equation to turn that into an optimal transport problem and solve also the Navier-Stokes equations. There's great richness in this problem that we are going to consider. And so, since this is such an important problem, Milan, Coda, Leon, and Jean-Bernard Lasserre looked at it very carefully, and they proposed for us a way to solve it using the Lasserre hierarchy. So basically, you start with your problem, that the original problem you want to solve. It's some PDEs, some variational problem, an optimal control problem, something of this sort. And you go to a Lagrangian formulation. And then you turn this into an infinite dimensional linear program using occupation measure relaxations. I'm going to explain this. And then I'm also going to tell you how to turn this into a hierarchy of tractable semi-definite programs. And here I just want to emphasize that the problems considered are very nonlinear, very non-convex. They may involve higher order derivatives, which arise from the Euler Lagrange equation. Not, although I'm writing only the first derivative, the problem may, in fact, have second order derivatives. And there's a way to generalize for other cases, also for higher order derivatives, but I'm not going to talk about that for now. And the method finds a global solution. It does not use any discretization or grids, and it really requires only very mild assumptions. So I think it's very interesting. So let me tell you how to do this. So we need to pass from in order for this method to work, we need to do what's called the occupation measure relaxation. And so we need to define a space that will have a couple of nice properties. This is, I'm going to define the space of occupation measures, OM. And so it will have representatives of all the Lipschitz functions, okay? So it's not exactly like the Lipschitz functions are contained there, but they will be represented. It has very good compactness and convexity properties that are crucial for solving this kind of problem. So the motivation, we motivate the definition of this space. Let's take a Lipschitz function y, and so to y we associate two measures that will encode y and its derivatives. Okay, so the first measure, mu y, it's just the integral with respect to the Lebesgue measure of, so you take any function f, and when you integrate with respect to y, what you're doing is you're integrating with respect to x, y of x, and v of y. Okay? So the measure, the Lebesgue measure on omega gets concentrated on the points x, y, and dy, and this is the measure mu y on this space. Okay, and then we do the same on the boundary, but just with the x and y. And of course we're integrating on the boundary, and there is on the boundary the boundary measure that you use for the Gauss-Green theorems and Stokes and all that. So I think this should be familiar, right? And so by Stokes we have a relation of this sort for y. So it's an integral of the derivative of something on the bulk equal to an integral of that thing times the exterior unit normal on the boundary. All right, and I just want you to note that we can write that in terms of the measures we define. Okay, so it's going to be the integral of that derivative of something with respect to mu y equal to the integral of that thing with respect to mu y partial. And note how this works. Here I'm substituting x by x, y of x by y. Here too. And then the derivative gets substituted by z, because z is the space where the derivatives exist. Okay? Other questions? So So this is how we define the space of measures that we're going to be interested in. So instead of starting with functions, now we say, okay, so to each function we can assign these two measures that satisfy a constraint. So why don't we just consider the space of measures that satisfy that constraint? Okay, so this space it's a set of pairs of measures, mu partial, where then we think of mu as encoding what the function would look like on the bulk, and mu partial what the function would look like on the boundary. And so mu is a compactly supported positive random measure on the points x, y, and the derivatives, satisfying just the measure is the head measure of omega. And then on the boundary, we have the same. And they have to satisfy the constraint. Okay, so the constraint I'm just going to denote it as mu partial, and it's a constraint that needs to be satisfied. This is important for all test functions phi that are at infinity with compact support on omega times y. Okay, so they have to satisfy that this thing is 0. Okay, before we had equality here, so I just brought it to the other side. Okay, and so this space, this is the space of relaxed occupation measure. This is mu is the relaxed occupation measure, and mu partial is the boundary measure. And so what you need to have in your mind is that what we're talking about is pairs of measures mu partial, where now mu is encoding what happens here in the bulk. So this is omega, this is domain. And so mu is encoding the value of a function and its derivative, and mu partial is encoding what happens here on the boundary. All right. And so we relax the problem. We can have omega and y and z and their functions. And we write the same problem, but now on the space of occupation measures. Let me better put them side by side so that you see what changes. Okay, so instead of going on Lipschitz functions, I'm minimizing on occupation measures. And so now the integral is not over the Weg measure, but over the measure that really represents what we would say should be a solution, right? And the same here. And instead of having these things be directly satisfied, we say the support needs to be the support of mu. The mu needs to be supported on the zeros of f and the sublevel set of g, and similarly for mu partial. Okay, so this is a problem that's very close to the other one, and so what's great about this problem is that it's linear in mu and mu partial. Okay, and you see that this support constraints, you should be able to turn them very easily into a constraint. I mean, you can take the moment matrix, truncate it at some finite point, and then the support constraints, they translate into a constraint on the positive definiteness of those truncated moment matrices. With yeah, maybe I should. I see some skeptics, so it becomes something like you take the moment matrix with mu, it needs to be able to definite, and then if omega is something like this, then you want this, and then the same for mu partial, except that now mu partial is more complicated. You need to break it into different parts of the boundary, and then you need to also consider minus GI sometimes, because you want to be exactly on the boundary. But it's so the support things, they're fine, and the problem that doesn't look so finite dimensional is this one, because here you have all the functions. There's a constraint on the constraint of all the functions in an infinite dimensional space. But this is easily solved. You can just say, okay, I'm going to just consider finite dimensional polynomials, and so this becomes a linear constraint on a finite set of moments, and so this is basically a generalized moment. Okay, so this is tractable, that you can assume some Archimedeanity and apply the Lasserre hierarchy and solve this. So this is what happens. You start with your PDE, you go to Lagrangian formulation, you relax the occupation measure to get an infinite dimensional linear program, and then you truncate, and you get a hierarchy of finite dimensional semi-definite programs that are tractable. And how do you get your solution from there? Well, okay, so you have optimized over measures, you truncate those, you get moments, and then you want to recover the support of mu, because the support of mu is what gives you where the solution should be, right? So in order to recover the support of mu, there's a new book by Jean-Bernard Lasserre, Edouard Powell, and Mihail Putina that explains to you how to do that with using the Christoffel function. And that gives you then an approximation of what the solution actually is. So this basically means that the only question we have left is whether it's legitimate to do this relaxation, because otherwise we could solve the problem and we're very happy, right? But we did this, so we have the classical problem, minimization over Lipschitz functions, and the relaxed problem where we're minimizing over these pairs of measures. And then, okay, so then we have this inclusion, kind of, right? I mean, it's clear that for each Lipschitz function, there is a corresponding measure. And so that means that the relaxed problem minimum will be smaller than the classical one. And the question we wanted to address is, do we always have equality, or is this relaxation going to give us going to have a gap and then give us some wrong results, I guess you could say.
So what do you say it's a relaxed? It's a dual one.
It's I say it's relaxed because well, you have representatives for all the Lipschitz functions, but not only that. In particular, you have complex combinations of several Lipschitz functions, and you have other weird stuff. So let me show you an example. So if the Lagrangian is not convex in Z, so for example here it's not convex in Z because it's this one. So I'm in one dimension. Already in this case, it's kind of trivial to find gaps. There is going to be a difference. Okay, so let me show you how this works. It's okay, this is the simplest example that can be shown here in 1 minute. And so it's a little absurd, but bear with me. Okay, so we take the minimum, we're just minimizing over integrating this thing from 0 to 1. And this is subject, I'm going to say subject to y equal to 0. Okay, so what functions are there? What Lipschitz functions are there that satisfy y equal to 0? Only y equal to 0. So the minimizer has to be y equal to 0. Its derivative is 0, so the integral is the integral here. So the integral here, MC, is 1. Okay. However, if we are considering measures, so we take the measures for the same Lagrangian, the integral for the same Lagrangian, and we assume that the support, so this subject to y equal to 0, this is the support being on y equal to 0. Okay. And of course, the Stokes type constraint needs to be true. And so the minimizer in this case is a combination of two measures. So at each point, it's going to be, it's like as if the curve were moving forward and backward simultaneously. Okay, it has position, sorry, value is 0, but the derivative is +1, and -1. These are direct delta. Okay. And so this is as if you had a curve that's oscillating infinitely fast. And in that case, well, you're integrating here and here, so the integral is 0. Okay, so the relaxed minimum is 0, and the classical minimum is 1. Yes.
0, 1 or -1?
It's 0, 1. So this is the z coordinate.
Yeah.
Yeah. Yeah, this is a problem of this subject that you need to be able to see at least in 6 dimensions. Okay, so of course this example is a little forced and a little absurd, but there's a better example that doesn't require much. I mean, it doesn't have a restriction, condition like that in the recent paper of Fantuzzi and Tabasco that I listed here. Okay. All right. Other questions? Sorry. No. All right. So since the non-convex case doesn't make very much sense, we now change our question slightly. We say that we always have the relaxed and classical minima are the same if Z is convex. Sorry, if L is convex in Z. Okay, and so what have people done? In the one-dimensional case, it was solved a long time ago, and this is solved using maybe you guys know it. It's superposition principles. There's a famous one by Ambrosio. There's also one by Smirnov. There are many, and in fact, okay. So this has a long history, and so. So if the domain is dimension 1, then yes, you have equality always. If not, then okay, there's a big literature, and I just want to cite a couple of interesting papers. So there's the interesting paper by Marx, Weiser, Ariane, and Lasserre, where they consider, I would say it's a very interesting paper because it's kind of complementary to this one. They consider a slightly different type of solution using some entropy inequalities, and so they can have discontinuous solutions, but still it works quite well. And closer to solving this kind of question, there is the paper of Chernyavsky, Ramboga, Fantuzzi, and Glushkin, where their method is heavily dependent on the form of L. It needs to be quadratic in Z. And so basically they use some elliptic equations to decompose the measure that's found as a superposition of solutions of the elliptic equations. And so for elliptic PDEs, there's a lot of theory and they leverage that. But then of course, Milan told me that there was this important poema final workshop, and he told me we have to solve the problem because there is this important event. And so I said, no, but it's going to be hard. And so, but he insisted. So yes, so we did it. And so our result is that indeed, not only when n equals 1, you have equality, but also when the codomain is of dimension 1, basically when your solutions are real value instead of vector value. And we found that there are examples in all other cases where you do have a vector. And so this is what I want to explain to you in the rest of the talk. In our paper, we also treated the optimal control case, which I haven't explained to you, but if you're interested in optimal control of PDEs, all of this, these results apply, and I'm available to tell you how to do it. And we also found examples showing that there might be gaps where you don't have only equality or inequality constraints, but also integral constraints. If there are integral constraints, there are also gaps. So just so you know, this is also contained in the paper, but let me explain to you how the paper works. So So the first part is the positive result on the m equal to 1 case when the codomain has dimension 1. And so in order to get this result, what you need to do is you decompose measure mu into a convex superposition of measures that are induced by Lipschitz functions. The convex superposition means that there's a probability measure on the space of Lipschitz functions, and you can express your measure mu as that thing. Okay, so this part it's the hard part of the paper, and it's agnostic to the optimization problem in question. So even if you have a problem that is not convex in Z, this part will still tell you something. Okay, it's just the final results. Well, we needed to use Jansen's inequality a little bit, and so we added that hypothesis. But the way it works is, okay, so you decompose like that, and then well, that means that by the converse of the Choquet theorem, it means that the Lipschitz functions correspond to the extreme points of the convex set of occupation measure, relaxed occupation measure. And so see this functional that we're basically functional we're minimizing, or also with the other part, the integral of mu partial, this is linear in mu or in the pair. And then the extreme are attained at the extreme points which correspond to the Lipschitz function. So we're done. We show we show that there's the way you show that there's no gap. So the hard part then is decomposing this measure. And so how do you decompose this measure? So imagine you have your measure that's encoding several different functions. It's like 1/3 of this and 1/3 of this and 1/3 of this maybe, or you know, something like this. So how do you find them? And it could be very ugly, right? It could be really ugly. It's just, I mean, we have very little hypothesis. So you look at this, you look at this, you look at this, and you notice, there's a reason why Rodolfo put some colors here. And the reason is that these guys are basically the boundary of the level sets of a function. So you look for a function rho such that each of these sheets is going to be the boundary of a level set. Okay. So, and then you look at this and you look at it very carefully, and you say, okay, if I'm moving in this direction, rho would be basically increasing every time I touch a piece of mu, right? So I need to have something like this, like a derivative. The derivative of rho should be something like mu, right? Okay, this doesn't make sense like that, but there's a way to make sense of it using the distribution theory point of view. So you take a test function, okay? In fact, for convenience, I wrote the test function as the primitive of a function, okay? So you take your test function and you substitute that thing, okay? You change the mu for 0 dy, and then you integrate by parts, and you get that. Okay, so that's what you're thinking that you should have. And so this is the key idea. In fact, you define a linear functional that's this, and then you use the Rodolfo-Rios theorem to show that this corresponds to integrating with respect to a density, which is your rho. Okay. So that's the key idea. This is an idea that we were able to adapt from work of Pitts and Swartzky, and it was very fruitful. So you find your function rho, whose such as the boundary of the level sets are going to be the functions you're looking for. And the function rho turns out to be a function of bounded variation, which means that it satisfies something like this, that the integral of rho times the divergence of any vector field that's smooth and small enough, it's bounded. And then there's a result for a function with bounded variation that says, called the co-area formula. It's very famous in the field. It says that the sublevel set of these functions are sets of finite perimeter, locally finite perimeter, actually. Meaning here, locally finite perimeter. So they satisfy a condition like this. This set, this sublevel set. And so what we need to show is that the boundary is nice, that it corresponds to a Lipschitz function, right? The boundary of a sublevel set. So how do we do that? Well, the Georgi proved something that's really useful. It's he proved that for every set of finite perimeter, there's you can basically do the Gauss-Green theorem. There's a measure and a vector field eta that give you the right thing to integrate with, which is house of measure. And so there's a bit of complication, but we're you know, if I'm putting lots of details under the rug, we're finally able to show that this is indeed equivalent to a condition of weak differentiability, which then implies that the functions are Lipschitz because the support of the measure is bounded. So, okay, so that's the first part of our theorem. And then the second part, we showed that we constructed an example with a gap. So let me show you how this example works. So we constructed it in the case in which the domain is dimension 2, and the codomain has dimension 2 as well. And so we constructed the Lagrangian such that the infimum over, okay, this is Taubalier functions of type 1, 2, this contain Lipschitz function, so this is a little better. This should be a little smaller than the other one, so this is okay. And this is going to be bigger than the uniformly bigger, right? This is the hard part. It needs to be uniformly bigger than the minimum over the measures. And so we're going to have what we're looking for, right? And so how do we do it? Well, we cannot just have a combination of functions. That doesn't work. So here I'm in this drawing, this is omega, and what I'm going to try to portray for you is what the solution for the minimization problem will be, because that's how we thought about this. We first found a good solution, then from the solution we construct the appropriate Lagrangian, and then the hard part is showing that there's a gap, right? So there's okay. So we take these two disks, we pinch them so that they meet at the middle. We cut a slit on each of them. We glue them together, and we glue the other two together. But since we're in dimension 4, there is no actual intersection. Okay, this is important. This will not work in dimension 3. So then the Lagrangian we construct is of this form. It's a quadratic thing for the y, a quadratic thing for the derivative, and then a little thing away from them. So okay, so here I guess you can see that there's basically a double covering of the disk. So the function that goes from the disk to this thing on top, let's call that u0, and the one that goes from the disk to the bottom, let's call that one u1. Of course, bottom and top don't make sense because this is R2, but you see what I mean. So basically, this u will be equal to u0 or to u1 if y is close to u0 or u1 respectively, and v is going to be the corresponding derivative. And so this thing will vanish exactly at the points when y is u0 or u1, and it will also be 0 when when the derivatives are what they correspond. And then g is a non-negative function that's going to be 0 close to the graph of the solution, but it's going to be positive when you're far away from the graph of the solution. And so that way we're just forcing the solution to be the one I drew in the previous slide. And so the minimizer is exactly going to be just half of the measure induced by the part on the top of U0, and the other half is the solution on the bottom. So it's a measure that is made up of both.
Rodolfo?
Yes.
Oh yeah, I'm confused again. So why do you need these two functions, U0 and U1? Why wouldn't it be enough to have just one? And I didn't get that.
Yeah, so if you had only one, then this would be a Lipschitz function, and it would be you would not get the gap. So there needs to be a four-dimensional problem, a four-dimensional obstacle. So in fact, yeah. And so, okay, so the Lagrangian is not negative. So the integral of this is not negative, and so you see it's made of things that are concentrated exactly where. So it's U0, this guy is U0, and we're and same for U1, and also for the derivatives. So and then G is also 0. So basically, it's the integral of 0. So the minimum is 0 for occupation measures. Okay. So for occupation measures, it's 0, and the problem now is just to show that if we take the infimum over the Sobolev space, we get something bigger. Okay, so in fact, our intuition, well, I think the intuition should be this should be true because H had to jump, and then so if you need to be on the U0 or the U1, otherwise this is big. But then you can tell me, okay, you jump quickly. But then I tell you, jumping quickly is not enough because then this will be big. Okay, so you need some relation that gives you a constraint on how much you jump with how big you're going, and this which will so basically, yeah, if you're far away from here, then this becomes bigger. Well, sorry. Yeah, the integral of that. So this is what we use, the Poincare-Oettinger inequality. The problem with the Poincare-Oettinger inequality is that it's for stuff that's in dimension 1, and it's not so easy to apply. So okay, so this is what happens when you have a candidate of solution. It's there. It's glued to one of the two coverings, and maybe it goes to the other one, but then it needs to jump, right? And it's this jump that should produce a problem, and so the way to finally apply the Poincare-Oettinger inequality was a little complicated, but we found that if we chose an angle alpha 0 such that the mass of this is our solution, sorry, candidate for solution for minimization, such that if most of it was close to this side and close to that guy, they were big enough on both sides. I don't know. This is hard to explain, but and then we truncated. So we define this thing, and we apply the Poincare-Oettinger inequality to that thing. And after some additional details, we got the inequality we wanted. And now I just want to say, okay, fine. So there is a gap. This guy, its minimum is 0, and for this one it's a little bigger. But doesn't it seem in this case that the red thing captures what the solution should be much better? So I don't know about all applications, but I think there should be many applications in which the measures are better than the functions. So I think this is all very interesting for the algorithm. And so just to recap, I explained to you how to go from a PDE variational or optimal control program and solve it using the Lasser hierarchy. And our main result is classification of the cases in which there are no gaps and where there may be gaps. And that's it. Thank you very much.
Thank you very much. Couldn't get back one second.
Yeah.
This theorem of yours,
Yes.
you made no assumption on the convexity for F and G.
Assumptions. Okay. Yeah. So yeah, there are some assumptions. The assumptions are really that the sense where you're restricting your z's to me should be so whenever you fix x and y, and you look at where the f, your equality is satisfied and your inequality is satisfied, that should be convex. And the same for the boundary, and they should be closed. Sorry, not the same for the boundary.
And so you shown at the beginning this univariate example with the gap.
Yes.
You see this
Yes.
non-convex
The W.
so yeah,
Mhm.
it's non-convex. So it's L which will be non-convex.
So L is convex, but only in Z.
Yeah.
Not really assuming. Okay. You can have a definitely a potential. You can have a,
Yes.
a magnetic field. You can have anything. Yeah.
I actually have two questions.
Yeah.
First, the conceptual. So you have a PDE,
Yeah.
just analysis.
Yeah.
Let's say it has a unique solution.
Yeah.
And when you replace it by minimization problem, if the PDE is a constraint. So how can you guarantee that you get the same solution of the original PDE?
Well, if it's the minimum on the set of measures, it will be the same. Otherwise, that's
You reform it as a convex consolidation problem and use unique solution, the solution of the PDE.
So we have, okay, so then your constraint is that
Then it's convex.
because you don't have any control variable there in the analysis. So
I see what you mean. So, first of all, you will find an approximation, right? So, you're turning your PDE into a constraint on the moments of a measure, and so in order to get exactly the same as before, you will need infinitely many moments. But
I think that,
Right.
But the second question was, you don't need any discretization.
it may also be a nonlinear constraint. No, we don't use in this script.
The advantage of
them that they don't.
things like finite element methods is that it can capture any kind of domain, geometrically complex. So here, what is omega? What can omega be?
Okay, so for this method, it has to be an Archimedean semi-algebraic set.
Semi-algebraic.
Yeah.
So you need, yeah. Okay, so you first need to find a representation of
As polynomials, yeah, but I think it would be challenging to find an application where this is not the case, but maybe have one. Yeah. Okay. Yeah.
Still, okay, it's a mesh free, but you discretize the function space, the test function. You should take count element. So it's discretization, the level of taking moments of count element and functions. So, but you don't discretize geometry and domain. But the function space.
But the number of the functions which describe omega, polynomials, does it play a role in the solution? If it's a polygon with many sides,
Probably
For polynomial optimization, I think.
increases the size of the SDP, maybe.
Yeah, it's increasing the cycle rate.
Mhm.
Bernard? Is there a way to maybe by adding new constraints to make the gap, reduce the gap or to?
Yeah, so I think if somehow you can say that your measure should be single value. Sorry, that the solution, the measure is concentrated on a single point over each
But
X.
this translate into some constraints to what?
I mean, I can imagine saying that the variance in the y direction will be, will be 0, something like that.
Isn't it very dependent on the.
And it becomes nonlinear.
And that's exactly what we did with one now.
But,
For hyperbolic conservation laws, if you don't add these constraints that you were asking about, then there will be gap. And in this case, we had a so-called entropy inequality conditions. And this closes the gap.
The problem is to generalize this, if we're only at a scalar hyperbolic PD, and but not generalize to other types of PDs or to systems of hyperbolic PDs. I think it works with the so basically, we don't have a good type of constraint to add in order to close the gap.
But for hyperbolic, it's not well defined, not well defined.
Scalar hyperbolic.
But for elliptic, no.
The last question, please.
I'm still a bit confused by the choice of this functional L, because if the PD has a unit solution, it doesn't really matter what you choose, because you can just single point in the feasible set.
so the thing is if you use the constraint F to model your PDE, that's a little poor because you only have like a first derivative constraint. So for me, it's more interesting when the PDEs actually come from L, from the thing being a minimizer, because then you have to satisfy the order Lagrange equations, and it's those that really give you all this richness that I was talking about. So
could you solve shape optimization problem by this? This could be a natural phrase.
shape of I don't know what this is, but you can solve minimal surfaces.
This is very general fundamental. I wouldn't use this necessarily to solve a given PD, but I would solve it for an optimal control problem with PD constraints. So this is in the paper, but not in the talk. Or a very problems of different kinds where the PDs are maybe underdetermined, so there is nothing solution to it.
So in the optimal control, can you change the shape of the unit, or the function is G, which will come from the unit?
There would be some clever parameterization to force it in this setting, not as it is written.
Okay, let's thank Rodolfo again for this very nice talk.